Hello and welcome to today's lecture on the normal approximation for data, a topic sometimes referred to or often referred to as the normal curve. This is a very important topic in statistics, and it's one that we're going to discuss in a variety of different applications. And so today we're just going to learn about some basics of using the normal distribution. What is the normal distribution and what do you do with it? It's important to remember that the normal distribution is a theoretical ideal. It's not empirical. So we draw a distinction between what's theoretical and what's empirical in the following way. Things that are theoretical rely on mathematics to underlie their form and content, whereas something that's empirical is going to use actual collected data. So something theoretical is based on a mathematical ideal, a theoretical ideal, whereas empirical things, and we will apply the normal distribution in a lot of empirical scenarios, these empirical scenarios are derived from actual data. Just as a note, there are many other kinds of distributions besides the normal distribution, but we're just talking about the normal distribution. And those other ones are relevant, but generally apply to scenarios that are more advanced. And if you were in applying this material later, encountered a data set with a different type of distribution, you could easily look it up and with the tools from this class, assess the shape and find the more appropriate application for it. So don't worry about those other types of distributions. We are just going to focus on the normal curve primarily in this class. We'll discuss one or two others, but the normal curve is used very widely throughout, especially social research, because lots of variables are distributed on a normal distribution. And let's think about, before we think about those variables, let's look at some qualities of this normal curve. This normal curve here, and in fact, all normal curves, because they all have the same properties. And so the first thing to notice about this distribution is that it's symmetrical. So if you look at the center, which is 0, you can see that it's the same on both sides. Only a normal distribution like this is symmetrical. A skewed distribution is not symmetrical. So you remember a skewed distribution, which we discussed previously, has a long tail to one side or the other. This is not symmetrical. Another important quality of the normal distribution is that it's unimodal, which means there's only one mode. It's possible to have a distribution with two modes, and you should definitely be aware of this for this class. And it would look more or less like that. That's called a bimodal distribution. A bimodal distribution has two scores that are essentially tied for most common score. in a unimodal distribution, there's just one score that's most frequent, the mode, and the mode is centered at the mean and the median. So this is another important quality. The mean is equal to the median, which is equal to the mode. And as you'll see, when we apply this in some actual data and analyses, these only need be approximately equal, as long as they're not significantly different, which is a significant difference, is a statistical term, and we'll discuss exactly how to assess whether these are significantly different or not. But for now, the thing to remember is they should be approximately equal in a normal distribution. Another final thing to remember about this normal distribution is that underneath the curve, there is that 100% of the data is under the curve. You can also conceptualize that as a proportion of 1. As in, this is one whole variable. That's all of the data for one variable. And we can divide this into proportions, and proportions are equivalent to percents. A percent is just a proportion times 100. But it's very important to remember this aspect that it's 100% of the data is under there, because we're going to use that idea to divide up the distribution and to find different points. Another important quality of the normal curve is that because it has these other qualities we just discussed, it's possible for us to use this theoretical ideal to take data from a data set, from a variable that is normally distributed, and convert those data into standard scores, or z-scores. Or I guess it might be more precise to say, well, these are z-scores. Z-scores are a type of standard unit. Standardized units can be, as long as they're on the same scale, so standard units generally use the z-scale, or often use the z-scale in statistics, and you can compare across different distributions by using these qualities. So now let's think about how the normal curve is a probability distribution. As we discussed, the curve is smooth, it's symmetrical and unimodal. And a final point is that to remember is that it describes a distribution of values. So here you can see how we have applied a normal curve to a histogram of real data here in the figure 2. And here we have a histogram for the heights of women compared to the normal curve. And you can see in the areas where the bars are clearly still outlined, that the heights follow a generally symmetrical normal distribution. They're unimodal. You can see the mode is not quite exactly the same as the mean, but it's only very slightly off. It's still pretty fair to say that these data are normally distributed. And we can use this information, information we know generally about the standard scale and about standard units to, for example, know that what proportion of the population falls between heights of 60.5 inches and 60.6 inches. Oops. Does anybody know what percentage I'm looking for here? Any ideas? We talked about this a little bit in our last lecture. I know we haven't discussed it much today, but this is getting at that idea that we know what proportion of the distribution lies between 1 standard deviation from the mean, 2 standard deviations from the mean, or really at any proportion of this distribution. So we could say what proportion of, or what percentage of the population is below the mean. 50% is on a normal curve. Now that might not be exactly true for these actual data, but an important part of understanding how we apply this is that we would, in applying the normal curve to a data set like this, we take these scores, approximate them with the normal curve, and then we can use the things we know about manipulating the normal curve to find these approximate percentages. So in this case, for example, the approximate percentage of the population between 60.5 inches and 66.5 inches is back to this idea that within above and below 1 standard deviation lies 68% of the population. So I can say with relative certainty that 68% of the population approximately lies between these two values. Let me just draw your attention back to this embedded piece here and this first figure. So I've done that, oops. I do this sometimes when there's really important information from the text that, of course, this is not a substitute for reading the text, but this contains some real pertinent information here. So usually I leave these pieces like a small embedded figure in the PowerPoint, and then if you use these slides to review, you can see that I highlighted this information as especially important. Why is this information so important? Because I really want to make sure that you realize that you need to know these values, period. You need to know them for the exam. Stat students always have to know these the percentages of the area that are between these locations on the normal distribution at each set of standard deviations from the mean. And just to look at this a little bit more, we can see that with 2 standard deviations from the mean, here, we'll put this over here, there's 95%. So that's as illustrated in this graph. And it's again an approximation, so it's not exactly going to be that proportion if you figured it exactly for a actual distribution, but we safely use this assumption all the time in statistics. So you can assume that once a variable is established as normally distributed, then it's safe to assume you can do any of these calculations and functions that we discuss in today's session and in this chapter. So the first step, although we're going to get in more to finding these proportions under the curve, but before we do that, I want to make sure we're clear on converting scores to standard units. This is, again, a very important skill. Expect to see this material again. Again, this is something you will want to be able to do on the exam. So we know if we want to convert a score to standard scores or to standard units, we're going to use Z, and remember the formula is X minus X bar, or a raw score minus the mean, divided by the number of cases, or N. Okay. I'm going to proceed with using the formula shorthand, but I've written it out here to help you with the conversion. So let's just quickly look at a couple of these scores. If we convert them to standard units, let's look at 60. We need to know a couple of values before we go into starting these calculations. We need to know the mean, and we need to know the standard deviation. And I'm using S to represent the standard deviation. SD is also fine, but for brevity, I'm going to use S, which is the standard notation for a standard deviation. So to convert this now, let's just go ahead and convert 60 to standard units. So we would take 60 minus our mean of 50 and just divide by 10. And we can see here the math is not hard. 60 minus 50 is 10 over 10. So this is going to give us a z-score of 1. Other problems can be done similarly. The math is a little bit, you might have to use a calculator for some of these other ones, but let's do one more because I want to do one calculation that's going to end up below the mean. Or I guess I gave away the end here, but we know that this one is above the mean because scores that are above the mean are always positive and scores below the mean are negative. And so we can see here, I guess you still shouldn't need a calculator for this one. Again, we have 45 minus 50 is going to be a negative 5 over 10. So here we have a z-score of negative 0.5. Incidentally, when you're writing up numbers that are just decimals, please always put the leading 0, that's this 0 right here, include the leading 0 in your when you're writing it out in whatever form you're writing by hand or in Word, because it's very difficult to read these numbers without it. Also, it's standard scientific notation to include the leading 0. And I personally need it because my eyes are bad and it helps make it easier for me to read. And now let's try one of these from B, finding the scores in which the standard units are already established. So we're going to go backwards to find those scores. To get the formula to go backwards, we just simply do the, oh, why did I put N down here? Nobody caught me. Boy, I can't believe it. This is the SD. I just got, this is the standard deviation. It's not N. You can win an exciting prize if you catch me making a apparent error like that. So keep your eyes out. If you see something that seems amiss in a formula or in a problem solving, ask a question, because maybe you'll have caught, let's call it an Easter egg of error, and you can win a special prize. But you've got to catch it to find out what the prize is. So I've corrected our formula here, x minus x bar over the standard deviation. And so then when we go back to convert from standard units or to the score, or standard units to raw scores, we just do the inverse of this formula, or z times the standard deviation plus the mean equals x, or the raw score. Whoops. And you could prove this algebraically, but I'm not going to worry about that. So we can easily find which score, the raw score for a standard unit of 0. What is the raw score? If you've got, for these data, if you've got a z-score of 0, what's the corresponding raw score? Well, this one should be quite obvious. I'm surprised there's not more cheers out there, because thank you, Stephen, it's 50. If you have a z-score of 0, it's always equal to the mean. In this case, the mean is 50. So we already know this one is 50. We don't have to go through any of this math. But if we want to, let's practice one other one. We have 1.5 times our standard deviation is 10 plus the mean is 50. So 1.5 times 10 is 15 plus 50 is 65. We'll see how we're converting in between those scores. Does everybody feel comfortable with doing this part of the calculations? Because we're going to need to do it a lot. Okay. Thank you, Tyler. I'm going to assume if you're not responding that you are comfortable. So now let's look at some practice finding areas under the normal curve. So we've established that the normal curve corresponds to reliable areas or proportions of the population. And so we're going to apply this in several different circumstances. Before we jump into that, let's think just a moment about some data that's normally shaped. And as an incidental point, yes, a normal curve is the same as the so-called bell curve, and let me stress this, don't use the bell curve terminology. It's racially loaded, as in it's based on some research that had some significantly racist undertones, to say the very least. So we're going to stick with the normal distribution. You can call it a normal curve. Let's stay away from the bell curve. Now these figures and these examples are in the OpenStax textbook that I mentioned before as a nice extra resource if you want some additional examples of how to apply this material, if you want to look at some other ways of framing it, feel free to look up the OpenStax textbook. And there's some nice examples in there. I generally use it for extra examples and ideas. So it's a good one to go with. And if you have questions when you're looking at it, feel free to ask me. It's more mathematical than our text is. So a fair warning. And here they're making the point that if you ask enough people about their shoe size and then graph their data, it's shaped like a normal curve. And the same can be said of other aspects of other personal qualities like weight. Weight may not be normally distributed in the US population. I don't know. Americans are really fat. Weight used to be normally distributed, may or may not be anymore. Height is normally distributed, as we saw in our earlier figure. Lots of personality traits can be normally distributed once they're measured. If we measured introversion versus extroversion, like how socially motivated someone is. Also, lots of health variables are normally distributed. So we might say this is where when you look at variables like temperature, like everyone knows that average body temperature is 98.6 degrees Fahrenheit. But that doesn't mean that every single person is uniform, got a body temperature of 98.6 degrees Fahrenheit. Their body temperatures would vary slightly depending on various variables, but they are distributed around that mean, and the mean is 98.6 degrees Fahrenheit. So some people have a body temperature that's slightly lower than that, some slightly higher, and once people deviate far enough from that curve, then we might, then later in the class, we'll find out, later in our course, we'll find out how to determine whether a difference is significant or not. That is, what values represent a significant difference from our expected or from the population known average. And we'll use the normal distribution qualities to find that. And here we have a normal distribution. It's laid out just like our other one, and I'm going to introduce you to a couple of terms in here. We're not going to use these, but you will see them if you use the OpenStax textbook or most anything. I might even, I'm trying to avoid the Greek letters this semester, but it's hard because I have years of using the standard symbology. So standard symbology here, which you should be aware of, is that we have this little guy here. It's pronounced mu. It's equal to the mean, specifically a population mean. We also have sigma, this one here. And these can be handy to know, so even that our book avoids using these symbols, it can be real handy to know when we get later on where we will have scenarios where you have to distinguish between population data and sample data. And one way to do that easily is that population data uses Greek letters to represent terms, whereas sample data uses Roman letters like X bar. Sigma is the standard deviation of a population. And so that's all they've laid out here. And that's all they're saying. He has this 1 standard deviation, 2 standard deviations above. And now here we can see that we have an example of how to divide this distribution. And this shaded area tells us the probability that X, a particular, this raw score here, oops, X box, I'm just making that up. That's not a term, but I thought it was funny. So they're saying this is the shaded area represents the probability that X box, just to help us distinguish between these two, is less than X. X is over here, the highest value in our data set, or the top of the distribution, we might say. And we can find the area of this portion of the distribution, as in this purple area, and then that area represents the exact probability that a score falls at or below this point. And now we can see this applied here with some numbers. So we have a distribution with a mean of 63. And we know that a proportion of 0.34 or a percentage of 34% lies above a score of 65. We also know what proportion of the distribution or what percentage lies below a score of 65. And what percentage is that? I'm talking to you, Peanut Gallery. Remember that this distribution represents 100% of this, the area under here is 100%, the whole distribution. And so if we want to know, thank you, it's 66. If we want to know what proportion lies below this score, well, if we know that this is 34% here, then the corresponding other portion of the distribution must be 66%. And this corresponds to a proportion of 0.66. So really, I just want to hit home that percentages and proportions are essentially interchangeable. You're just at multiplying or dividing by 100. So 66% lies below a score of 65. Now we have shaded the lower portion of the distribution. And here is the proportion of the distribution below a score equal to K. So this is what they're saying. The shaded area represents a probability of 0.9. Well, where do they get that probability? That probability corresponds directly to the proportion. So we can say that, so I know, because I know that since this is a probability, this is telling us that there's a probability that of 0.9 or 90% that a score will fall at or below K. So this probability K being this score here. And it's simple as that. If you know this proportion, and I know this proportion is 90% or 0.9 as a proportion, because that's what the goes hand in hand with knowing the probability. So if you know the proportion, you know the probability. What is the probability that a score fell above K? What percentage of scores were above K in this distribution? %10. Exactly. So we're just going back to using this same quality that we know there's 100% under here. So if I know a portion of that 100%, I know the corresponding other portion. And now here's a somewhat trickier scenario. So in our other scenarios, we could see that the distribution was, our shaded proportion was at one or another tail of the distribution. But here we've highlighted just a portion of the distribution, this area in the middle. For whatever reason, we want to know the proportion of scores that fall between these points, 1.8 and 2.75. And so we can find that too if we find by using our Z table to find the areas and corresponding, let's see, is this one got, and their corresponding proportions. We're missing a piece of information here that we need to convert these scores to, or to know what these proportions are, because they've plotted here for us the raw scores, but we don't know what these z-scores are. So in order to first find this proportion, I would need to know the z-scores for these other values. I know the z-score for 2 because 2 is the mean. That's clear. And so the z-score is 0. In order to find the z-score for these other values, I need one more bit of information that's not available here, and that's the standard deviation. So here we have a mean of we know x bar is 2, and the standard deviation is 0.5. So we can easily find this proportion, what proportion of the distribution lies between these two scores, and these data are supposedly the amount of time in hours a household personal computer is used for entertainment. I find that hard to believe. It seems kind of low to me, but I'm going to guess that they made up these data because actual data on computer use is much more frightening. We spend countless hours in front of screens. So the first step to find the proportion of the population that falls between 1.8 hours and 2.75 hours is to find these to convert to z-scores. So first we have 1.8. And remember, to convert to z, we use the formula z is equal to x minus x bar over the standard deviation. And so this first one is 1.8 minus 2 over 0.5. Feel free to do the math for me while I set up our other conversion. 2.75 minus 2 over 0.5. Okay. Did anybody find this first z-score? All right. Well, when I do the math on this, I can see that this first z-score is negative 0.4. And the second one we can just calculate out. You could make this a lot more fun if you calculated along with me or even ahead of me. That's really fun. Why is it fun? Well, because it's rewarding and reinforcing and makes you feel good to get these numbers faster than me. So try it in the future. I strongly encourage and greatly value your participation. So now I can plot these scores, and we don't have to plot them, but it is very helpful to do so. And I'm going to recommend doing that, generally speaking, throughout this course, because we're going to use this idea later as well. Finding these scores based on proportions. So if I know these scores, then I can just I can use the z table, and I guess I'm getting a little bit ahead of us, aren't I? But that's fine. We can use the z table to find the proportion of the distribution that lies between these scores. And I'm going to use this opportunity to introduce to you a different z table than the one in your book. It's already on Blackboard. So in the course content area of Blackboard, in the resources folder, I've uploaded a table. It's the only thing in there. And it has in it a more user-friendly Z table than the one in the back of your book. And I'm going to go ahead and use that one today, and you're welcome to use it. It does not matter what Z table you use. So if you found the one in the book intuitive and you liked it, well, that's fine. You're welcome to keep using it. But if you thought otherwise, which I did, I'm going to use another Z table. The Z table is standard, so that's a great thing about it. I could use any Z table I like, and they're all going to have the same scores and the same proportions for each of these Z scores. And so in this table, you can see how they've laid out these proportions quite nicely. And here in column A, we have the Z scores. In column B, we know the mean to Z. So this is the middle column here. And column B measures the area from the mean to a z-score. And column C tells us the area that's outside of a z-score, the area beyond a z-score, whether that's above or below. So we can use this to find these proportions and locations on our figure here. So first, let's find the this first z-score, which is 0.4. We can follow along on our z-table until we get right here to the z-score, 0.4. And then I know that the mean to z area, or the area, from this proportion here is 15.54% of the distribution. And I know also from this table that the area beyond z, or this area down here, is 34.46%. So that's the area from here down to the end of the distribution. But we need some more information than that in order to solve this problem. So let's keep moving on. We next need to find our other z-score in the proportions of the distribution for it. And there's two different ways to solve this problem, at least. And I'm going to show, so I'm going to show you two different ways to address a problem like this. So I'm just following along this table. I'm looking through column A for a z-score of 1.5. And I know this might be a little bit hard to read on your screen, but remember, the table is available on Blackboard, and you're welcome to go and download it right now. In fact, I would recommend doing that because we're going to use it more during this lecture. So we can see here that at a z-score of 1.5, the mean to z proportion is 43.32. So that is now the proportion that goes from the mean here out to our z-score over here. And that was 43.32. And I know one other bit of information. The proportion of the distribution that lies out beyond a z-score of 1.5, and that corresponds to, or this proportion here, and that's going to be 6.68. Just a pause here. Can you hear that lawn equipment outside of my house? Okay, great. I can though, so I'm gonna go and shut that door over here. Hi, hello, kitty. Yeah. That's better. I'm afraid it is gonna get louder, so that's good. Okay, so back to our example. Now what we need to do is figure out, now that we know all of these proportions, you can see probably one easy way to do this would be to take our mean to z for our first mean to z for negative 0.4 to the mean, 15.54, and add the mean to z for the other side of our proportion of interest, which is 43.32. If we do that, we can find that the proportion of the distribution, or the percent of the distribution. Does anybody already know? Thank you, Tyler. 58.86. Oop. And so that's our total proportion here, this total area. And I also know that the probability of a score falling between these 2 points of someone, the probability that a randomly sampled person from the population, the probability that they use their home computer for entertainment between 1.8 hours and 2.75 hours, well, that probability is going to be equivalent to this number. Probabilities are expressed in units between 1 to 0, so it would be we would divide by 100 to get that probability. But it's going to correspond directly to the percentage. So we could find this. Yeah, Tyler, I think that the one that this alternate table I've given you is a lot easier to use. I think the one in the book is non-intuitive. So I definitely encourage using the alternate chart here. The other way that we could find this would be to say, we could use these values to manipulate this distribution in other ways. So if I know that, for example, this proportion out here is 34.46, then I know the corresponding proportion over here is approximately 66. That is the distance from, oops, let me get a new color. So if this is 34.46, this is approximately, all of this is 66%, again, approximately. So I could find, I'd still have to find these points, but I know that this, if I know this is 66%, then to get this proportion, all I need to do is take 66% and subtract out the area beyond Z for our upper limit. And we would end up with the same answer. Okay, just a couple of ways to think about that. So any way of adding or subtracting these proportions, which gets you to the shaded area, is valid. It's just important to remember what area of the distribution your proportion represents. Any questions about this idea? Oh. Okay, excellent. And just one more figure here with an example about, which we've pretty much discussed this idea already, but to reiterate, the shaded area represents our probability. And here we have the probability that X is less than K. Where's K? They didn't even label K. This must be K here. And so they're telling us this proportion of the distribution is 0.25. And this area over here is 0.75. The probability of a randomly selected person falling into the probability that a randomly selected person has a score well, this is obviously not K if K is 1.66. I'm not sure. Let me see. Oh, they're saying what K, this is not a standard score. K is a raw score. So this represents 1.66 hours of entertainment time that the computer is used for. Okay, so we could find the z-score for K here, 1.66, but we already practiced doing that, so suffice it to say, let's assume that we already found the z-score and we know, actually, we don't even need to do any calculations. If we know that this proportion of the distribution is 0.25, we can go to our z-table, and this is another important application of the z-table, and if we find the proportion of the distribution that's, we can use column C to find a proportion or a percentage of 25%, and that's going to tell us the z-score for K. So let's do that. And here I am in the C column, the area beyond Z is 25.14, or we could choose 25.83 or 24.83. You always have to choose one of these values. We would never pick one in between. So I'm going to go with 25.14, or the z-score of 0.67. So you can see if you look across the column back into the A, if you look across the row rather, for this location in the table, you'll see the z-score is 0.67. So isn't that handy? And this is an important application to remember. It's really important to remember these various ways you can use the distribution to find scores or proportions. Okay. And I did put in here some more exercises to look at the area under the curve. Do you want to do these exercises, or do you feel pretty good about finding the area under the curve? I'm going to say that yeah, if you're not leaping at the opportunity to find these areas, I'm going to assume you feel comfortable with this idea, and I'm going to reiterate one more time. You'll definitely want to know how to do this for the exam. And this is more information. You really, just to hit home, you want to know these proportions of the distribution, these standard ones that are between above and below 1 standard deviation from the mean and 2 standard deviations, 3 standard deviations. And we already know the answer to this first one, the area plus or minus under the normal curve equals 68%. That's going to be between plus or minus 1 standard deviation. Now we don't know the area between, it's the area under the normal curve that's equals, or for B here, it's not one of our standard percentages. What we're looking for now is the area between the standard deviations between which 75% of the distribution would fall. And so just remember, when we're talking about these betweens, you need to find the centered proportion, not the top or bottom part. And so if we are looking for this bit in here, and we know it's 75%, then we know that the area out here, the area outside of that, shaded in light blue, we know that that's equal to 25%. So we could find this a couple of different ways. The one that comes to my mind most readily would be to take, you could either take 75% and split it in half, because this is centered on the distribution. So we can either say 75% divided by 2, which is 37.5. And then find the mean to z equal to 37.5. Or we could do the same process, or we could take our 25% and divide that by 2 and use the area beyond z, corresponding to what, 12.5. So I know that the total of these two areas is 25%, but each one taken alone is only, just this area is going to be only 12.5%, or 25% divided by 2. Oh, Candace, I see you want to do some of the exercises. We'll go back and do them in a minute. But let's finish finding the area between these, the area that encompasses 75% of the distribution, because we're almost there right now. So now I'm going to go back to my z table and look first at the area between the mean and z, and I'm looking for an area of 37.5%. And if you haven't already, I really strongly encourage you to download this table from our resources folder and do the problems along with me. Practice looking at the table, because we're going to use this table a lot and other similar tables. So here I am in the mean to z column. I'm looking for 37.5, or as close as I can get to it. And here I have it, 37.49. That's clearly as close as we're going to get. And it's a z-score of 1.15. So that tells me the z-score for these points is 1.15 and negative 1.15. And the way to answer this question would be to say the area between plus or minus 1.15 standard deviations under the normal curve equals 75%. And before we go back to the other exercises, let's just finish here. Number 3, I pulled out some of these problems from the exercise sets because I think they're especially relevant to practice. For your exam, not to keep, going on and on about it, but I do like to highlight very clearly things you need to know, and pretty much everything that if we discuss something in lecture, I consider it important, and mostly they are, it's fair game for the exam, but I'm specifically highlighting this material as an essential part of your exam preparation, let's say. And you definitely expect to do these calculations on the exam because they feed so much into what we're going to do next in class. The normal curve is sketched below, so we have two different ways of looking at the normal curve. We can either find the middle 90% or a percentile of 90%. So this is a percentile because it's the score at which 90% of the distribution is below. So to get this first one, we can use the same process as we did earlier. We know that this 90% is going to be centered around the mean. So I know that I'm going to have 45% on each side. And I can just use the Z table to find that 45% in the mean to Z column. And then use that to find the corresponding Z score. And here I am back in the table in column B. I can see that at 45%, this is a score of 1.65. And then the corresponding negative Z-score would be 1.65. So 90% of the distribution falls above and below a Z-score of 1.65. Or plus or minus, I should say. I should say plus or minus 1.65. And over here, now we're going to use our Z table a little differently. So I know that if this is 90% of the distribution in this shaded area, then out here I have just 10%. And so we can go back to our Z table, and this time we're going to look in column C for that 10% in the area where column C has 10% in it, and that's a Z-score of 1.28. Any questions about the distinction between these two areas of the distribution and how to find them? Okay, well, let's practice it a little more. And if you're out there thinking, why doesn't she just get to the review exercises? Well, because you really need to feel really solid about these earlier exercises. This is one of those times when you really should feel pretty good about doing all of these different exercises and these different applications of the Z table. So it's worth our time, and it will pay off in the end for us. What does it mean to pay off in the end? Well, of course, I'm talking about the end being your grades, right? Or an exam. I'm talking about some relevant measure to you when I say things like that. And so now we're going to find the area under the normal curve. And to do these, I'm going to grab this normal curve from our other slide because I don't draw normal curves very well, or it's quite hard actually to draw them. I'm using a Wacom tablet here, and it's tricky to write or draw very well with them. It takes a lot of practice, and I'm still working on it. So I appreciate your patience with my diagrams, my handwritten work. So let's find the area to the right of 1.25. Well, first let's get ourselves centered around this distribution. So I know that here's my mean. This is just to help us navigate a little bit. And the mean is 0. And we want to know the area to the right of, well, let's just label it as our mean, but it would be the same. It's the same thing whether I put 0 or X bar there. Now we want the area to the right of 1.25. I'm just guessing here, but I'm going to say 1.25 is approximately here. And to get the area to the right, I'm asking you now, what column of our Z table will we use to find this area to the right of a Z-score of 1.25? Are we going to find that area in column B or column C? Make a guess. It really doesn't matter if you're wrong, but somebody guess. Thank you, Candace. I appreciate that. You're correct. It's C. So we just go to our Z table here and look at column C. Well, first we're going to find our Z score because we just want to know, we already know our Z score is 1.25, and we want to know what's the area to the right of 1.25. It's simple. It's going to be 10.56. It's there in column C. Actually, I'm going to switch colors between these examples so we can keep drawing on this curve, and this way you'll know which color is which. Next we'll do B. What's to the left of negative 0.4? Well, a negative score is going to go below the mean. 0.4 is going to be a lot closer to the mean, maybe about here. And again, we can just go right to our Z table, look up a score of 0.4, and which column are we going to use this time? Oops. If we want to find the area to the left of 0.4, we can use the column C again, because we want to know the area that's beyond this score. And so we just go back to our table. And here I am at a score of 0.4, and the area beyond C is 34.46. Okay. To know what's to the left of 0.8, we can find 0.8. Let's say it's approximately here. Oof. You can see the trend. If we want to know what's to the left of 0.8, we can just look in column C, where we find our Z-score of 0.8, and then look at column C, and the area beyond Z is 21.19%. Now it's going to get a little trickier here on D. because we need the area between 0.4 and 1.3. Now we did something like this earlier, so try to think through yourself, how do we, oh, we didn't do one quite like this. So now we have one that instead, both of the scores are above the mean. And we need to find the proportion between them. So we've got a score of 0.4 and 1.3. And so to get this proportion, it's going to be a few more steps. Oof. Okay, I cannot stress how difficult it is to draw a straight line like in this process. So I'm really trying here. Assume lines are straight, are smooth lines. So we need this proportion between these two orange points. And we can find this a couple different ways. I'm inclined to, I can see that the easiest way to start is with some things we already know. So I already know at a z-score of 0.4, the area beyond z is 34.46. So that's all this area here is 34.46%. But in order to find the area between these two z-scores, I need to subtract out the area that's beyond a z-score of 1.3. So let's go find the proportion of the distribution beyond a z-score of 1.3. So I'll go back to my handy dandy z table. And at a z-score of 1.3, we know that the area beyond z is 9.68%. So to get this proportion right, that I'm shading in yellow here, the proportion between our scores, we're going to subtract out this 9.68 from the total proportion beyond 0.4. So I have 34.46 minus 9.68%. And if you really want to win a thrilling prize, you'll get this number before me. Ooh, but I'm fast on the tail of this proportion. It's 24.78. For the future, you can win thrilling prizes like a kitten or a crane. I mean, an actual kitten or an origami crane. I'm just teasing about the kitten, unless you really want a kitten, because there are a lot of kittens around me. There's a lot of land around me, so of course there's cats, and I found some adorable new kittens just recently. I know, so if you or someone you know wants a super adorable kitten, I did bring them into the house and we're taking care of them until they get a little bigger and we can find homes for them. They're adorably cute. Oh my gosh. And my two cats are like really taken to mothering them. That's crazy how much. Kind of hilarious. So they're well socialized. But anyway, and since I'll see some of you in person, you really can win a genuine origami crane folded by me to be distributed at our next lecture. They're pretty sweet. Those are just a couple of the thrilling prizes you can win for your engaged participation. So just as a point of interest, we'll get back into Collaborate soon. We're using BlueJeans right now. And in Collaborate, there's a function where I can pop up little questions for you, and we can take a poll. So when I keep asking you questions, those are points where if we were in our other originally planned platform, you would have a couple of multiple choice options available. So try to imagine there's a poll there, and just make a guess as you can. We'll be back and Collaborate hopefully with our next lecture or so. And so does everybody see how I found this percent before I move on to E, this proportion here? Okay, good. Oftentimes people find this really tricky, and you really do need to do all of these different things in various applications later. So we have two more left. We have this E here where we can find the proportion between negative 0.3 and 0.9. Note that I'm choosing colors in keeping with the order prescribed by the rainbow. Why am I doing that? Because there's an internal hierarchy of color. When you're color coding something, that internal hierarchy goes Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And so when you have an internal hierarchy in a variable, it's nice to stick with the internal order if you can. And so that's what I'm doing as we're going through these. Although I didn't start with red, I am following the spectrum color changes, except that we can't really use yellow because you can't see it. We could use brown instead, but anyway, so yellow would be there, but yellow is too hard to read. And I don't have a dark yellow option here. And I suggest using a similar strategy in your notes. You're going to have a lot of things where there's an internal order to the process. So if you're color coding things, keep in mind Roy G. Biv and the natural color spectrum to help you embed organization in your notes. Why is that helpful? Well, because then they're easier to navigate, but also it helps your mind take the material in more readily. The mind loves organized things more than chaos, and more readily learns things that are organized than learning chaos. So just a little tip. So here we are at E, and we have a score of negative 0.3. It's getting kind of packed on this diagram. I know that. Sorry. And 0.9. Oh, not bad. I'm trying to use a ruler. Oh, look, it didn't even like my line. Jeez, PowerPoint. Okay. I guess PowerPoint doesn't take kindly, or the tablet doesn't take kindly to using rulers to write on it, or to write, make your line straighter. So now we're just trying to get this proportion here. And we can just do this by getting the mean to z for a negative 0.3 and the mean to z of 0.9 and adding them together. And I'm hoping that at this point that's already clear. So do we want to go through and actually find these, or are you feeling pretty clear about how to find the values now? Okay, thank you, Candace. Please don't be afraid to say, let's more practice. That's fine. I just don't want to keep practicing things that you already feel confident about. That's all. So it's fine. It's good. If you want to practice more, just tell me and we'll do it. Imagine if we were in the same location live, I'd be able to see from your expressions how you wanted to proceed at these points. But remember, I can't see your faces, so you have to tell me what your faces say or what your mind says. So here we are in the z-table, and I've had a z-score of 0.3, and the area from the mean to z is 11.79. And that's this proportion between, remember this is our z, I'm not going to draw another line in here because it's starting to look like a prison in that normal distribution. A colorful prison, but a little bit difficult to navigate. So this proportion here, right, was 11.79. And then we'll get the other proportion here, oops, from the mean to a z-score of 0.9. And I'll go to a z-score of 9, or 0.9 rather. Here we go. And the mean to z is a percentage of 31.59. It's this area here. And so if we want to find this total area, we can just sum these two proportions. So again, that's going to be 11.79% plus 31.59%. And let's take a look. And we know this proportion, the percentage is 43.38. And just to circle back on our proportions, we also know the proportion of the distribution that lies between those scores. The proportion between a score of negative 0.3 and 0.9 would just be would be equal to this percentage divided by 100, or 0.4338, right? One more left, and we are back at blue, but I'll use this other blue. And now this one will be simple to find. We need to know the proportion outside negative 1.75 to 1.75. So here's negative 1.5. I know I said 7.5, didn't I? Whoops. And here's a positive 1.5. And what we want to find is the area that's outside of both of these scores. Boy, those aren't correctly positioned on this distribution, because obviously these two scores are in the same location, are symmetrically located. So for the sake of a little bit of accuracy here on this one, I'm going to replot these just because it was so badly off before. Okay? And what we need is the proportion beyond these points. So this proportion and this one summed together. So to do that, we'll go to our Z table and find our Z score 1.5. Here it is. And then the area beyond Z is 6.68. I'm looking in column C, and I know that then the area beyond Z is 6.68%. So if I want to know the area that's outside of both of these scores, then I would just multiply this by 2, because I've got 6.6% over here and 6.68% over here. Or you could think about it as, you add the two proportions, but they're the same. So you can just multiply by 2. And we know that the area is 13.36%. Thank you, Candace. Okay. Phew. So now we know how to find all these different proportions and areas under the normal curve, and we're going to need to know this for lots of topics in the future, and we'll work on some applications right now. So we have I've selected this problem from exercise set C. Actually, Stephen requested this problem, but it is a good one. So let's look at it. And let me take a quick look ahead. I think we're going to do this problem, and then we're going to take a brief break and come back and do the review exercises. Well, we're going to do this problem, talk about one more very brief topic, then take our break for just a couple minutes. I'm running out of tea. So we have here women aged 18 to 24 in Haynes 2, which they describe a little bit, the Haynes data set. It's now, the study has evolved into NHaynes, and it's similar to the GSS survey that we've been looking at, and the data is available publicly, and it's another data set that we are going to talk about at some point in lab, and it's a good one to be aware of. I know we have a lot of nurses in the audience, and NHaynes is the Nutrition and Health Age and National Health and Nutrition Examination Survey, I think, something like that. We always use these acronyms. Sometimes it gets hard to remember all the acronyms, but NHaynes this is what I'm talking about, in case you're interested in learning more about it. It's a useful data set, and it's got a lot of great health data in it, and it's a really nice survey that I know we were discussing before, Jay, some of the powerful ways to leverage these skills. And Haynes is another real powerful population survey. So back to our exercise set. We're looking at just women 18 to 24 in Haynes 2, and their average height was 64.3 inches. And I'm going to start out by taking note again of my important data over here on the left. 64.3 inches, and the standard deviation is 2.6 inches. And now we can use the normal curve to estimate the percentage of women at each of these height levels. And so this is a very common application of the normal curve. And let's look first at A. So we want to know the percentage of women with heights below 66 inches. Well, the first thing we need to know is the z-score for 66 inches. Z is equal to x minus x bar, the raw score minus the mean over the standard deviation. And so the formula for that would be 66, in this case, our conversion formula, minus 64.3 divided by 2.6. And see how I've written out the formula and then the applied formula, the formula with our substituted values. I usually do this below. So the best way to do this, what I'm getting at, is that you don't just write these equations once, you write them every single time that you do them. That's why every time I convert a z-score, you see me writing this equation again, and you'll see every time we do an equation, I'll write out the equation, if we're doing it by hand. Why? Because we're going to move into places where we have equations with lots more values in them. And you want to make sure you're keeping track of your values and where they go in the equation and working everything out correctly. Because I'll tell you what, mostly people, when we get into the more complicated equations, mostly people's mistakes are small errors, like losing a number here or there, not big things. So that part of preventing small errors is just rewrite the equation. The other benefit to rewriting these equations when you use them is that it helps to embed the material in your mind. And obviously that's an important piece. I'm furthermore writing it below, and I think I wrote this out backwards anyway the first time. I'm writing it below. It's a good reason why you should write it out, because when you write it below the equation, then it's easier visually for you to make sure that the values you're substituting in are matching in with at the right spot that they're supposed to be. So now let's go ahead and work this out. For the top, I get 1.7 divided by then 2.6 for our numerator. And we end up with a z-score of negative 0.65. Great. We solved our part 1 here. We know our z-score. And the next thing we're going to do is use our z-table to find the score and the corresponding area beyond z. Yeah, Candace, I did write it out incorrectly the first time. It's x minus x bar. X is our raw score minus our mean. And you can see that I reversed the values. That kind of mistake where you reverse two things that like that, it's a really common error, not just for me, but it's a common error that people make. And it's another reason why you should write out your equations like this and solve them step by step below, or vertically rather, I mean to say. See, there's another example of switching up two things that are dichotomous. So below 66 inches, we're going to go to our Z table as I laid out here and find a score of 0.65. Oh. Oh, there we go. So here in Z column, we have 0.65 and the area beyond Z is 25.78. And just to make sure we're doing this right, let's draw a diagram to help us visualize what we're doing. Don't be afraid to draw a diagram. Look at how poorly drawn mine are. They don't have to be perfect. It's just a visual cue. And it'll help you from making simple mistakes. Here's our mean. Our z-score is below the mean. Let's say it's here, negative 0.65. And we want the area below that, so this part out here. We just looked up that percentage, and it was it roughly 25%? Yes, 25.78. Boy, pretty soon I'll have the whole z-table memorized. And that's the answer to our question. The percentage of women with heights below 66 inches is 25.78. Now we can follow a similar process to find the part B, the area between 60 and 66 inches. So first we convert each of these to z-scores. Z equals x minus x bar over s. And we have 60 minus 66 over 2.6. And our other z-score, we already know the z-score for 66 because it's 0. Oh, no, wait, for under 66 inches. Oh my gosh. Candace, you're right. I'm sorry. Geez. did exactly the error I was talking about earlier, even talked about it, and then still did it. The formula is the formula. It's x minus x bar, and the average height was 64.3. I mixed them up, and so in my fixed version of the problem, I'm going to remember that, and this would be obvious, should be obvious, because I would be expecting 66 to be a score above the mean. So this should be, and I apologize, but it's a great example of how you can catch yourself. X, the score we're looking for. She gets a cat. Candace, you get a cat. Joe, you get a cat. Everybody gets a cat. Please, please, everybody take a cat. And so similar issue here, we can just take our similar solution, 66 minus 64.3. It's 1.7. And that's what I meant by similar. It's going to be corresponding, so it's just a mirror image of it. So instead of being negative 1.7, it's 1.7 over 2.6. And we end up with a z equal to negative, or not, equal to 0.65. And now we want the area below 0.65. Let's assume this is more or less 0.65. And we can figure this out. We don't need to refer back to our z table. We already know that the area beyond z over here is 25.78. So to get the area below this z score, we can just take 100 minus 25.78. And it's 74.22%. That sounds much better to me. Starting to run out of space here. But that number was 74.22. And I'll, for posterity, fix it over here. Always remember to label the units on your calculation. The units here being percentages. Whew, so we did all that, and it was useful because now we know the correct z-score for 66 inches. Z-score of 66 is equal to 0.65. And we'll switch to green for B. So we just need to find one z-score. 60 minus 60, I'm going to get it right this time, 64.3 over 2.6. And now my numerator is negative 4.3 over 2.6. And we get a z-score of 1.65. And this is the z for 60. Let's put this on a curve. We'll put over here. Oops. In our 66, we already have the z-score for 66. It's, oops. Let me plot the mean here. Here's our mean. 60 is below the mean, so this is a negative 1.65. And 66 is above the mean, 0.65. We want the proportion between these two. We already know this proportion out here is equal to 25.78. And that the proportion below this is 74.22. So we can use that information we got for part A to help us find the answer to B here. So if we know that this whole area here is 74.22%, then we can just find the area beyond Z for a z-score of 1.65. That is the area down here. And then we can use that we can subtract that area from 74.22%, and then we'll have this interval between our two z-scores of interest. Oh, 1.65. I'm just going to a z-score of 1.65. Eventually, I recommend, if you can, print out this table. You might want to print this whole set of tables that are in this PDF, but you'll want to have a printed copy of this. I do at home, but I mean, I am at home, but we're looking at it on the screen now. You'll want to have your own printed copy. It makes things a lot easier. So the mean to z proportion here is 45%, approximately, in the area below. Beyond that z-score is 4.95, or so we can take 74.22 minus 4.95, and that's going to give us our proportion here. A kitten for whoever gets this first. Oh, will you please relax? I thought someone was at the door. Somebody get it? Oh, I guess I'm stuck with the cats. 69.27. Oh, Candace, boy, you're really racking up the cats. And here's one now. Okay, 64.97. I think we should take our break now. The area that's, so we can see that this proportion is 69.27. To get the area above 72 inches, I think do we feel good about that? I'm dying for a little break, so I'd love to stop here unless there's any objections. Okay, Let's take our break and we'll reconvene in a few minutes.